Today we're going to look at the second lecture of chapter number 10, and the chapter basically still discusses dynamics of rotational motion. We always start with learning goals, and the learning goals for today's lecture, the first one, define the angular momentum of a particle or a rigid body. The second is learn how the angular momentum it changes with time. And finally, use the angular momentum conservation law to describe rotation. So let's start with how we look at angular momentum. We already looked at linear momentum in chapter number 8, and we defined linear momentum as equal to mv, mass times velocity. Now, in angular momentum, we're also going to involve, because there will be circular motion, or you can say rotational motion, we're going to also involve in how far the object is from the axis of rotation. So if you, let's look at something that's performing a circular motion here, like this mass m here. This mass here, it will have a velocity v, so it will have an angular, it will have a linear momentum mv. Now, if this is a circular motion, you know that we always take the tangential velocity. So it is tangent to the circular motion here. So for this mass m, you have a linear velocity mv, and it is a r away from O, where O is basically the point where the axis of rotation goes through. Now, like what we did in the last lecture when we talked about torques, we're going to look at the moment arm, or the lever arm, which is perpendicular to the linear momentum. So if you extend this all the way, and you take L, which is perpendicular to this line, and when we talked about torque, we said this is the line of action along which the force is acting. And we, if the angle, if this line here along the linear momentum makes an angle phi relative to the position vector r, so this L here will equal to r sine phi. So in the same way, if now we define angular momentum, which will equal to mv times L. So in this case here, the angular momentum will be mv r sine phi, because the L here is equal to r sine phi. And that basically is your angular momentum now for this particle mass here, m. Now, we can relate this to the position vector and the linear momentum, like what we did in the case of the force and the position vector for the torque. So we can rewrite this as mv r sine. We can rewrite this as r mv sine phi. And of course, you can take this if you regard r as a vector and the momentum as a vector. So you can say that L here will equal to r cross t sine phi, where phi is the angle between both of them. Now, look at your linear momentum here. If you extend the position vector here, you will find that the linear momentum make an angle phi, because of your geometry, this angle will be phi as well. Now, you look at the components of the linear momentum, one which is along the position vector here, and you will say that's mv cosine phi, but that's not going to affect the rotational motion. But if you look at the one that's perpendicular to it or tangent to it, you will find it's equal to mv sine phi. And this is basically, it makes an angle 90 degrees with your position vector here. So like what we did in the case of the vector now, we can basically look at the linear momentum and the position vector, and we can write our angular momentum here as r cross p. Of course, your L here, which will be the magnitude, it will be r, and your linear momentum will be mv, and of course the angle between both of them will be sine phi. And that will be the magnitude of your angular momentum. Of course, you know the direction will be perpendicular to the plane made by the position vector and the linear momentum. That's a cross product here. And you have to use the right hand rule to decide on the direction of your rotation. Remember, in this case, if it's moving this way, it's counterclockwise, and that will be around the positive z-axis here in this situation. Now, so the magnitude is going to be r mv sine phi, or you can write it as mvr sine phi if we just want to look at what we have here in the diagram. But if you rewrite this as r mv sine phi, then that basically we can get to the angular momentum is equal to r cross p. And of course, you will use the right hand rule to decide on the direction of the rotation. In this case, it's plus the z-axis because I told you it is rotating counterclockwise. Now, the SI units for the angular momentum, well, the mass will give us kilograms, and the velocity will give us meters per second, and r will give us meters, so it will be kilogram meter squared per second, and these will be the units for the angular momentum. So the definition now for angular momentum, it is r cross p, where r is the position vector, how far is the particle from the axis of rotation, and p is the linear momentum, which is equal to mv. And since it's a cross product, you're going to use the right hand, and the direction will be perpendicular to the plane formed by the position vector and the v here, because the linear momentum is mass, and mass is a scalar multiplied by the velocity, and the SI units will be kilogram meter squared per second. That's our definition for the angular momentum. Is this clear? Any question on these? Here we're going to look at an analog to Newton's second law. Let's look at the rate of change of the angular momentum. So if I want to take dl by dt, and since L is equal to r across P, which is r across with mv, so if I take the derivative, I will take dr by dt across by mv plus r across with m dv by dt. Now, dr by dt will give you 0 because the particle will be fixed there, okay, at that position vector. It's not going, the magnitude is not going to change. Now, then r across dv by dt, and dv by dt here will give you a. So you get r across ma, and ma is the force. So dl by dt will give you r across f, and you know that r across f, this is equal to the torque. So your dl by dt will equal to tau. If you recall what we did in chapter number 8, in chapter number 8 we said that f equals to dp by dt. So the force here is related to the rate of change of linear momentum. The torque here is related to the rate of change of angular momentum with time. So you can see here, that's why we say analog to Newton's second law. So if you just look at what we did in the last lecture, we said that tau is equal to R cross F. Today we defined L as R cross P. And here we say that dl by dt is equal to what? It's equal to tau. Is this clear? So that's how we relate angular momentum to torque, as we related linear momentum to the force in chapter number 8. Now, let's extend this to a rigid body. And we said in rotation, when you take a rigid body, that means the body is not going to be stretched or deformed under rotation. And let's take a point mass m here on this body here. And we look at our origin here. And the body is in the xy plane. And it's rotating about the z-axis, where the z-axis is pointing out of the page. So it is rotating counterclockwise with angular velocity omega. Now, you know, when we said that V should equal to R omega, that's what we did in chapter number 9 when we related tangential velocity to angular velocity. So if you look at this point mass here, it will have a tangential velocity Vi, which equal to Ri omega. And we said that for rotation, or a rigid body in rotation, omega, alpha, and theta will stay the same. They're not going to change. So, and it's R away. So when we look at our linear, when we look at our angular momentum, and we said the angular momentum is equal to mvr, because this angle here is 90 degrees, and sine 90 degrees is equal to 1. So it will equal to mvi here will equal to Ri omega, and of course the R will equal to Ri. So it will give you mi Ri squared multiplied by omega. That will be the angular momentum for mi, where mi is point mass on this rigid body here. If you want to do it for the whole body, then you're going to choose different points as point masses, and you can basically make these masses equal. So what you do is you can sum over all of these, where you can say that I here will go from 1 to some value that you're going to choose. So it will be the summation over mi Ri squared multiplied by omega. Omega is going to stay constant. You know that this value we've seen before, and we call this the moment of inertia. So your angular momentum here will equal to I omega in general. So it depends which way it is rotating. So you can have clockwise rotation, a counterclockwise rotation will be positive, a clockwise rotation will be negative. So you can decide in which direction is the angular momentum. Is this clear? Now you're going to use the right hand rule. And the right hand rule, we've seen this before. You can basically don't use the left hand, use the right hand. You curl your finger in the direction of the rotation. And in this case, if you look at omega here, it's rotating counterclockwise. And your thumb is pointing up. Now, it depends on your choice of the axis. If you choose the x-axis to be this way, the y-axis to be this way, that's the plane, and the z-axis basically pointing out of the page. So you can say that your wheel here, it's in the xy, it's in the xz plane, and in this case, your angular momentum will be pointing in the positive y direction. Now, if your wheel here is rotating in the clockwise, and again you choose your x-axis to be this way, y-axis this way, and the z-axis this way, so that means this is in the xy that's zxz plane, and this is the y. So the rotation here will be what will be the negative y direction. Now, sometimes what is done, they basically shift the z here to a y pointing out, and of course this will be z, and in this case this will be negative z. The same thing here, you can change this to y, and you can change this to z, and of course this will be positive z. Well, you have to look which is counterclockwise, which is clockwise, okay, and you can decide on the direction of your angular momentum. So is this clear on how you decide on the direction of the angular momentum? Now, let's take an example here to do calculation of some of these. Example 10.9, a turbine fan in a jet engine has a moment of inertia of 2.5 kilogram meter squared. So they give us the moment of inertia I. About its axis of rotation as the turbine starts up, its angular velocity is given by, and they tell us omega z is equal to 40 t squared. So it is rotating around the z axis. A, find the fan's angular momentum as a function of time and find its value at 3 seconds. B, find the net torque on the fan as a function of time and find its value at 3 seconds. What we're given omega z, which is equal to 40 t squared, and we're given Iz, which is 2.5 kilogram meter squared. So by definition, my angular momentum is equal to I omega, but since it is rotating around the z-axis, so Lz here will equal to Iz omega z, and I is equal to 2.5, and your omega z is 40 t squared, so that will give you 100 t squared. Now, if you want to evaluate that at 3 seconds, you put 3 squared, and 3 squared is 9, and that will give you 900 kilogram meter squared per second. Is this clear? Is this clear? So that's basically now your angular momentum. In B, they ask about the torque. You know that torque around the z-axis will be dz by dt. So it's a d by dt of 2.5 times 40t squared. And of course, 2.5 times 40 is 100. So you're taking d by dt of 100t squared. And d by dt of t squared will give you 2t. So this will give you 200t. And t at 3 seconds will be 200 times 3, and this will give you 600. And you know that the units for a torque is in Newton meter, because you know that torque is equal to R cross F. And the units for R is meter, and the unit for force is in Newton. That's why we have a Newton meter, and we dealt with this in the last lecture. Is this example clear of how we looked at angular momentum, and the rate of a change of angular momentum should equal to the torque? Now, what happens if the net external torques on the system is 0? Remember, we said that dl by dt should equal to the torque. But if this torque here is equal to 0, then you have dl by dt is equal to 0. meaning that L here, the angular momentum, is going to be constant. That means L1 is equal to L2, or L before should equal to L after, or L initial should equal to L final. And you know, we defined L, we said L should equal to I omega. So if you're looking at 1, so it will be I1 omega 1, of course, around the z-axis. You can do it around any axis here. And I2 will equal to omega 2z, or it could be the x, the y, it depends. Okay, and this is in the case when you have zero net external torques. We've seen a similar relation in chapter number 8 when we said that F should equal to dP by dt, and when we have no external forces, we said this is equal to 0, and that implied that P1 should equal to P2. That's in the case of linear momentum. This is now in the case of angular momentum. Is this clear? Any question on this? Let's take an example here. Example 10.10. A physics professor stands at the center of frictionless turntable with arms outstretched and 5-kilogram dumbbell in each hand. He is rotating about the vertical axis, making 1 revolution in 2 seconds. So he makes 1 revolution every 2 seconds. Find his angular velocity if he pulls the dumbbells into his stomach. So we want the angular velocity here. It's equal to what? His moment of inertia without the dumbbell is a 3 kilogram meter squared with arms outstretched, and 2.2 kilogram meter squared with his hands at his stomach. So now we have 2 different situations here. That's the axis of rotation, and again that's the axis of rotation. So the arms outstretched, the moment of inertia here is equal to 3 kilogram meter squared. When he brings the arm in, the moment of inertia here, it's equal to 2.2 kilogram meter squared. In this situation, he starts with 1 revolution in 2 seconds. Now they ask us what is the angular acceleration when he pulls his arms toward his stomach. Well, you know that moment of inertia is basically a distribution. So if you look at the dumbbells here, the distance here is 1 meter. And when they bring it this way, the distance is about 0.2. So you know there is a change. There is a change in the moment of inertia. Now we have no external torques. You don't see any forces here, but you can say basically I have a gravity which is pulling down. You have the normal force which is basically pushing up. But they are on the axis of rotation. So R is equal to 0. So both of these will give you 0. So that's why we say the torque due to the force of gravity equals the torque due to the normal force, which is equal to 0. So we have 0 external torques here. So we are justified in saying that L2 should equal to L1, or L final should equal to L initial, or L after should equal to L before. So you know that the angular momentum is equal moment of inertia multiplied by the angular velocity. So in 2, it will be I2z omega 2z. We'll choose the z-axis as our vertical axis here. He's rotating around this axis, and we can call this the z-axis. And he's still rotating counterclockwise, so in both these cases positive. It's going to equal to I1z omega 1z. That means before. Now, I'm going to look at the moment of inertia 1 around the z-axis. It will equal to the moment of inertia of the professors when the arms are outstretched, plus the contribution that comes from the dumbbell. Now, the moment of inertia when the arms are outstretched is 3. And for the dumbbells, you have 1 on the right and the left. So it would be mr right squared plus mr left squared plus mr right squared. And r is equal to 1 meter when the arms are stretched. So it's equal to 5 times 1 squared plus 5 times 1 squared, and you get 13 kilogram meter squared. That's your moment of inertia 1. Now, when you look at moment of inertia 2, when he brings the arm toward his stomach, it will be now the moment of inertia of the professor when the arms at his stomach, plus the contribution that comes from the dumbbells. So it will be 2.2 for the moment of inertia of the professor, plus 5. Now the dumbbells are 0.2 away from the axis of rotation. 5 times 0.2 squared plus 5 times 0.2 squared, and that will give you 2.6 kilogram meter squared. So that's your second moment of inertia. Now from this one here, we can basically look at the angular speed after he pulls his arms in. So it will equal to I1z omega 1z divided by I2z. But what is my omega 1z? They told us that he makes 1 full revolution in 2 seconds. So it is 1 revolution over 2 seconds. 1 revolution is 2 pi divided by 2, and that gives you pi rad per second. So your moment of inertia 1 is 13, your omega 1 is pi, and your moment of inertia 2 is 0.26, and you get here 5 pi rad per second. So it is more. And now this happens if anything reduces its moment of inertia, but it conserves its angular momentum, then the angular velocity or angular speed, it will basically increase. Is this clear? Is this clear? Any question on this? So that's basically how we look at conservation of angular momentum. That's why when you look at skaters, when they bring their body in, they reduce their moment of inertia, and if they reduce the moment of inertia, they will be spinning faster. Now, in chapter number 8, we looked at example when we considered conservation of momentum of a bullet hitting a wooden block, and the wooden block basically swung like a pendulum, and from that we decided on the speed of the bullet. What we're going to do here, we're going to do something similar. You have a door, and a bullet hits the door exactly in the middle. The door, of course, has hinges, and when it hits the door will swing at an omega angular velocity omega. Now they ask us, what will be this angular velocity? So a door 1 meter wide, mass 15 kilogram, can rotate freely about vertical axis through its hinges. A bullet with mass 10 grams and a speed of 400 meters per second strikes the center of the door in a direction perpendicular to the plane of the door and embeds itself there. Now they tell us here, you remember when we talked about moment of inertia, we can look at the door and it's rotating around one of its ends. So the moment of inertia of the door here will equal to 1/3 md squared, where the mass here is 15 and d here will equal to 1. Now the bullet hits exactly in the center, so it is 0.5 meters away from the axis of rotation. And it comes in with a speed of 400 meters per second, and the mass is 10 grams. They ask us, what is this W here? So find the door's angular speed, and then is the kinetic energy conserved? Now we have no external torques, so we can say that L1 equals L2, and we know that the rotation here, we can choose the Z-axis, so I don't have to put the subscript Z here, okay, but it is rotating around the Z-axis. Now, momentum before, if you look at the situation, the angular momentum that I get here, it's coming from, I'm looking at the door, but what's causing the initial angular momentum? It's basically the bullet that hits the door in the center. So it will be equal to mvl. Mass of the bullet is 10 grams, which is 0.01. V, or the speed, will be 400, and L is equal to 0.5. That's how far is it. And this will give me 2 kilogram meters per second. 2 kilogram meters squared per second, and that's your initial or angular momentum caused by the bullet. Now, after the bullet is embedded, the door is going to rotate, but now it will be rotational. So it will be I omega. The angular momentum now is I omega. What is our I? The I will come from the moment of inertia of the door plus the moment of inertia that comes from the bullet. The door, it's 1/3 md squared. The bullet will be mr squared. Now for the door, it's equal to 1/3, 15, and d is 1 meter squared, plus the bullet is, the mass of it is 0.01 because it's 10 grams, and 10 grams is 0.01 kilograms. It is 0.5 away, so it's 0.5 squared, and that will give you 5.0025 kilogram meter squared. That's your moment of inertia. So 1 equals to 2. You can put a subscript Z here, okay, but I am omitting that because I told you from the beginning that we're rotating around the Z axis. So it will be MVL equal to I omega. Omega will equal to MVL over I. The MVL is already calculated. It is 2 kilogram meter squared per second. And your I is 5.005 kilogram meter squared. Now this will give you omega of 0.4 rad per second. And that's the angular velocity of the door. In B, they ask us, is the kinetic energy conserved? So we look. Initially, the door was not rotating, so the kinetic energy is only coming from the bullet, which is linear. So it's 1/2 mv squared. 1/2 times 0.01 times 400 squared, and that gives you 800 joules. Now, the bullet inside the door, and the door is rotating, so it should equal to 1/2 I omega squared. We already know that I is equal to 5.0025 kilogram meter squared, and our omega is 0.4 rad per second. We square that, we get here 0.4 joules. So the kinetic energy is not conserved in this case. Is this clear? Is this clear? Any question on this example here? So the idea here, we talked about angular momentum, and then we looked at the rate of change of angular momentum with time, and then we looked at conservation of angular momentum. Now, usually in the third part of the lecture, we always take some questions where we try to reason what should be the right option in these questions. And the question that we have here, a spinning figure skater pulls his arms in as he rotates on the ice. As he pulls his arms in, what happens to his angular momentum? I and kinetic energy. You know that the angular momentum should equal to I omega. And you know that the rotational kinetic energy is equal to 1/2 I omega squared. Now, you know that when the arms are outstretched, you have a moment of inertia. When he brings the arms in, the moment of inertia will be reduced. That means he will be spinning faster. Now, we don't have any external torque, so we know one thing here, that the angular momentum is going to stay the same. So if you look at our option here, they tell you L and K both increases. That's not right. L stays the same and K increases. So we can look at that as an option. L increases, K stay the same. That's not going to happen. L and K both stay the same. So on B and D, the angular momentum is conserved. That's fine with me, but I have to look at the kinetic energy. Now, is the kinetic energy is going to stay the same? Well, you know that when we did this in chapter number 6, when we talked about work, and we said that the work should equal to the change in kinetic energy. Now, when he brings his arms in, he's doing work. And that will change the kinetic energy. So the kinetic energy, it cannot stay the same. So we will basically find out that the kinetic energy is not going to stay the same. So we can take that option out. But the kinetic energy is going to do what? It's going to increase because you're adding now. With that work, you're adding basically to the kinetic energy. And that's why we say here that L stays the same, but the kinetic energy can increase. And you can work it out, by the way. You can look at your the change in omega and the change in the moment of inertia, and you can basically look what happens. So the answer here is B. Anything that basically reduces its moment of inertia, it will be spinning faster. That could be happen, let's say in astronomy, when we talk about the neutron stars, and neutron stars are spinning very fast because all the mass has contracted and it has a smaller size, and that's why you have a smaller moment of inertia, and because of conservation of angular momentum, well, it will be spinning faster. Is this clear? Now here we're going to look at the difference between linear momentum and angular momentum. So they're telling you a ball is attached to one end of a string. You hold the other end and you whirl the ball in a circle around your hand if the ball moves at constant speed. So you can say that you have a uniform circular motion here. But our definition of linear momentum, it's equal to mv as a vector. And you're taking about the tangential velocity here. And when you go around the circular motion, your velocity is not constant. Your speed is constant, but your velocity changes direction. So we cannot say that the angular momentum is constant. So the angular momentum is not constant. The magnitude of the angular momentum is constant. But the momentum itself, or the linear momentum, is not constant because v is going to change what? It's going to change direction even though your speed is constant. Now, when you talk about angular momentum is equal to r cross p. So r, the magnitude of b, and the magnitude of r, the magnitude of p sine phi. When you look at the circle, you'll find that they are perpendicular to each other, and sine 90 is equal to 1, so you get rp. So the value here, rp, magnitude will stay the same, but the axis of rotation in this case will be, if you're going this way, which is counterclockwise, that means around the z-axis, so your angular momentum is going to stay constant. But your linear momentum is not going to stay constant. Is this clear in this situation here? Now, let's take another question here. And this is something we can go back to the rotational kinetic energy. The three bodies in the figure below have the same mass and radius. They roll down to the bottom. Which body reaches the bottom first? Now, you know one thing, they're all coming from, and this incline that makes an angle theta here, it has a height h. So if you look at your initial energy, it should be kinetic plus potential, but they're starting from rest. So your kinetic is 0. So the only thing that your initial energy, E1, will equal to mgh. And it's the same for all three of them because all three objects have the same mass. Now, when they reach here to the end, your energy will be potential plus kinetic, but your potential will be 0 here because we chose this point here to be 0. You only have rotational kinetic energy, which is equal to 1/2 I omega squared. So if you equate both, mgh should equal to 1/2 I omega squared. Now, if you want to get your omega, you can multiply this by 2. You'll cancel this half. You divide by I. So mgh over I equal to omega squared. So your omega here will equal square root of 2 mgh divided by I, where I is the moment of inertia. Now, you look which one will have higher omega. That's the one that's going to reach first. Well, we did that when we talked about moment of inertia. For a solid sphere, the moment of inertia is equal to 2 over 5 mr squared. For a solid cylinder, it's 1/2 mr squared. For a hollow cylinder, it is 1/2 mr1 squared plus r2 squared. So you'll find that the moment of inertia of the cylinder, of the sphere, is less than the moment of inertia of the solid cylinder, and the moment of inertia of the solid cylinder is less than the moment of inertia of the hollow cylinder. So the sphere is the one with the lowest moment of inertia because we made a condition, m and r is the same for all of them. So what happens here, you will find out that the one with the smallest moment of inertia will be faster. And that's why our answer here is going to be what is going to be A. Is this clear? But we made a condition here. We said that the mass stays the same, radius stays the same. Is this clear? So in summary, what we did today, we defined what angular momentum is for a particle, and we said it's equal to R across P. For a rigid body, we said that L should equal to I omega. That's when you have a rigid body. And if we have no external torque on the system, we said that tau is equal to dl by dt. When the net torque on the system, it's equal to dl by dt. But when this net external torque is equal to 0, then in that case, you will have L1 equals to L2. And that's why we say here I1 omega 1 is equal to I2 omega 2. And we say that this is conservation of angular momentum. And that's the reason why when you look at ice skaters, they will be spinning faster when they basically bring their arms in because they're reducing their moment of inertia. Is this clear? Any questions on these? Any questions? Good.